So now we've got our chiral molecules, so we're taking a step back from our spectroscopy, our overall spectroscopies. We're going to go back and briefly look at our chiral molecules back in chapter 5. And in that, what we're looking at were these diastereomers and enantiomers. And one of the things that's going to become important is physical observations of these. So it's one thing that we can say that these things exist in structures, but do we actually have evidence that they exist? So let's think about the physical properties of, say, diastereomers. So one thing that wasn't super obvious in the past that might be relevant now is that diastereomers have to have at least 2 chiral atoms. And if we look at the structures here, we do have those chiral atoms. If you also go through and look at these, you'll note that we're looking at 2 different viewpoints of the same molecules. So these are identical relationships or identical things. So let's go through and look. This structure is identical to this structure, and this one's identical to this one. So why show these 2 different relationships? Well, if we're thinking about physical properties, for organic chemistry, the 2 biggest things that are really of concern would be our phase transitions, so melting points or boiling points, and it really doesn't really matter which one because you're getting the same principles for each, and solubility. So let's look at the easiest, which would be our melting points, our phase transitions. Solubility brings in a third or a second thing that we don't want to evaluate. So let's just look at melting points. So if we're considering a melting point and we look at it, well, we're primarily concerned about the intermolecular forces. And if we were to compare diastereomers, because they have the same formula and arrangement of atoms, their intermolecular forces are the same. And in this particular case, we're saying we have London dispersion forces because it's just carbons and hydrogens. So we say, well, they shouldn't have different melting points because same forces. But remember, with melting points, it's not just the strongest force, it's also a bunch of other things that contribute to that overall picture. So we could look at the dominant force within that molecule. Well, it's the same in this case. We could also consider like branching. How many branching? Because if we branch, that compacts the structure, which changes the surface area, which changes how it interacts with the outside world. Well, the branching here is about the same too. So it's like, well, again, no difference. Well, it turns out that we do have a difference here. That difference is not inherently obvious if we look at our overhead standard view. Okay, our overhead standard view being these guys. Where it's helpful to actually see that difference is if we shift to our Hayworth projections. And that becomes important because now we can see where those things are and get an idea of the relative shape of these things. Okay, so if we're looking at it, we've got one molecule that's acting as a plane with a piece up and a piece down. If we look at the other one, we still have that plane, but now both pieces are aimed up. Okay, well, is that going to change how this might interact with another molecule? If I was to draw another one here, I might align it like this, so that this way I can decrease that space in there. I can get a stronger stacking. If we go through and look at the other one, well, how do I align it? That's going to be kind of hard. I'm going to minimize that stacking potential, which could now change how those pure molecules could interact with each other, which means different melting points. So if I look at diastereomers, a pair of diastereomers, I would expect them to have different melting points from each other. Okay? Perhaps more relevant, if I mixed these 2 with each other, this is now going to be a drastically different system because we have different compound diastereomers, so different compounds. So it would be impure and we would get a broad melting point. But for sure, if we looked at each individual melting point for each of these substances, we would expect a difference. Okay? This manifests in all other attributes of these molecules. So if we were to look at solubility or how they interact with other molecules, we do see a clear difference in those properties because their shapes are inherently different. Okay? So if we were to look at, say, a lab reference to this, how could we identify which one we made? We've already kind of addressed it. We could use melting point. Melting point would be an easy way to go through and identify that we had one versus the other, and we would just compare them to the literature. If we had a mixture, we could see that it was a broad range. Okay? So melting point is a useful technique for us. We could really pull a couple different techniques out, but that's going to be the easiest one. Okay? That's if we have a pair of enantiomers. What happens if we have, diastereomers? What happens if we now say move to enantiomers? Well, enantiomers are a little bit more problematic. Okay? They're going to encounter the same issue as our diastereomers. Same strong forces, same secondary strength of forces within it. But then when we consider how they stack, they're going to stack the same, just mirrored. So for instance, if I had a bunch of right hands, I could layer a bunch of right hands next to each other. If I had a bunch of left hands, I could layer the left hands next to each other. If I compared between those, the stacks would look like mirror images. It's the same interactions in both cases. But if I brought the right hand and tried to layer it with a left hand, now it's going to be different interactions. Okay, so enantiomers are problematic because within a set, they're identical intermolecular forces. So you get the same melting point. So if I tried to say go through and determine which naproxen I had, remember S versus R from looking back, okay? S naproxen and anti-inflammatory. That would be useful to kind of cure some, headaches or body aches. R naproxen is a liver toxin, okay? That's kind of a big deal. Well, how would I know which one I had? Well, if we ran the melting point, there becomes a problem because the melting point for both S naproxen and R naproxen is identical. Their interactions with their outside world is also almost identical, and we'll address what that almost is in a second. Okay, you'll note that in some of these we're seeing these different responses. We're like, well, if they have identical interactions with the world, why are we seeing a different response? Why is one an anti-inflammatory and one a liver toxin? Well, when we consider that, we're not considering them interacting kind of independent on their own or with, say, a solvent like hexane. Right? What we're looking at them interacting with is the human body. Well, why would that matter? The human body is chiral. Virtually all of the biomolecules that we find within our bodies are chiral. Why does that matter? Well, our body is effectively a right hand. When it reaches out to grab S-naproxen, that interaction is inherently different than if it reaches out to grab R-naproxen. So two chiral species see each other differently. There's our interaction. Okay? That's why when we see S-naproxen, body. Smells, body. Okay? That's how your body responds to it. And because those molecules found within our body are chiral, they interact differently. And it's the pairing of a hand with scissors. But hands with hands, right hand and left hand, are going to have the same interaction all the way through. So I can't look at non-chiral interactions. I have to see how it interacts with a chiral system. A pair of right-handed scissors is going to stack with right-handed scissors very well. Left-handed scissors are going to stack with left-handed scissors very well. The only time I see a difference between them is when I layer right and left on top of each other. So chiral to chiral, I see a result. If I'm not actually mixing them, there's no difference in those interactions. And that becomes a lot more challenging to deal with. Okay, so the biggest deal, physical observation, identical for enantiomers. So how could we potentially separate them? Okay, so we will know, say, if we were doing naproxen, making naproxen, that we have both S and R because the melting point will be awful. Okay, and don't stress about that, but the range will be very, very broad because they don't interact well with each other. Okay, so we know we have a mixture. How do we separate that mixture? Okay, so here we go. Nice and easy. Step one, don't do it. Okay? The easiest way to avoid having to separate enantiomers, because they have those similar intermolecular forces, is to not make them. When you go through and run a synthesis, you want to ensure that you make only one of them, say the R naproxen or the S naproxen. I don't want to design a synthesis where both are made at the same time, because then I run into this problem of having to separate them and they interact with the world very similarly. Okay? That's the best method. Okay? Well, then what we could do is separate them on a chiral medium. Remember, we said ingesting it, you would see it, your liver fails, or your, pain goes away. You're effectively separating those on a chiral medium, your body. That's not a really good idea. We could pull out different techniques where we use a solvent that is, say, chiral, or we use column chromatography, a medium, a substance that is chiral that interacts differently. That's that right and left hand scissors with right and left hands. Okay, that will allow us to kind of separate those away from each other. So that is a useful technique. Expensive, but useful. The other one is going through and running a reaction. Okay, so doing a chemical reaction. One of the problems with chemical reactions is they tend to be irreversible. So we do have to be careful with the reactions that we run. We want them to be reversible, which is acid-base reactions. Okay, so what we would do is react our mixture, right and left hand, with just right-handed scissors. Okay, well, the right hand can grab the scissors, the left hand can't grab very well. I now have two different substances. I have a right hand with scissors. It's a good thing I don't have scissors. And I have a left hand with nothing. Well, now their interactions with the world are different because one has scissors in it, and I can separate those. That's the effective idea. If we look at what that actually means, this is what we're looking at, and that becomes kind of confusing to deal with. Okay, so let's break this down and look at what we're evaluating. Okay, so in the analogy that we just went through with the scissors, we said these were my right and left hands. We'll call it right and left, and we'll call this my hands. And what I'm reacting it with is my scissors. I think I spelled scissors right. Okay, and then we get a new result that comes out of it. Okay, and this would be our result of our hands with the scissors. The important part behind this is noting that our scissors have a very particular chirality, and in this case, we're using that R to represent the nomenclature system of R. Okay, what is the relationship that comes out of these? Okay, well, that becomes a little bit more challenging to deal with, so let's kind of label this out a little bit better. Okay, in that top case, we have that wedge, so it's still wedge, so we've got R hands with R scissors. If we look at the bottom case, we've got left hand with R scissors. Okay, what is the relationship now between those? Okay, well, if we consider through this, these are identical, these are mirror images. Before you start saying, they're enantiomers, no, they're not. Only one position mirrored. The other two stayed the same, which means the relationship between those structures is diastereomers. It is easy to lose sight of that analysis if you just dig in and look at the structures. Okay, so start pulling some information out so you could organize that process and recognize what's going on. So in this case, what we're doing is we're now converting those enantiomers, which we can't separate well, into a pair of diastereomers. Once they're diastereomers, they will now crystallize differently, and I can separate them based off of that different property. That's kind of cool. Okay, so rule 1, don't do it. Don't make enantiomers. Rule 2, use a chiral medium. Rule 3 is also using a chiral medium, but now a chiral reaction as opposed to intermolecular forces. And then rule 4 is effectively saying, F it. I can't do anything about it. Okay, so I've made these two things, but now I'm going to report how badly I did. Okay, that's not the greatest method, but at least you're being honest with that approach. So we would report according to an enantiomeric excess. Okay, well, what do we mean by that? We're talking about the excess of one versus the other. And we really have two enantiomers, R and S. Okay, so in excess, R over S or S over R, it's all going to kind of depend on that exact system. So if we look at the excess, it's defined as the highest enantiomer over the lowest enantiomer, which means if we look at the enantiomeric excess, it should always be positive, okay? Because it's always highest minus lowest. It does not mean that the enantiomeric excess will always be the R or S enantiomer. It's going to be one or the other. That's going to depend on which one was highest and lowest. Okay? And we'll see some fun calculations, fun being not fun at all, but we'll discuss those. They're pretty straightforward, though recognizing where all those pieces go. If you vaguely remember percent abundance, it's kind of like doing percent abundance. But that is for another video. So hopefully you got a basic understanding of what's going on with our intermolecular forces between our enantiomers and diastereomers, and we'll come back with how we can actually evaluate and see those things in just a second.